in on. Okay, so where we were is we were looking at our forces between charges. So if I have a positive charge and a positive charge, my forces are going to repel. And if I put another positive test charge here, that's going to want to repel from this one, and that's going to want to repel from that one. And so we'll end up with a net charge or a net force that's going to look something like this. It's going to go off in some other direction. I'm going to get at a net force that's looking at it. So that was looking at our electric forces. Looking at our electric forces. So our forces, remember, were K, Q, Q over R squared, and those are going to be in the direction of my R. Then last week, we also went in for my electric field, and my electric field, we defined as the force divided by our charge. So this was going to actually equal KQ over R squared. It's still in my radial motion here. I'm still going to be looking at it from that perspective. But now I can define things like, what does my electric field look like due to a line of charge? And anywhere along this point, we can look at, okay, I can put a positive test charge here. And I can have and be able to tell what's going to happen associated with that charge based on being able to look at it from that perspective. So this gives us our idea that I can have a dipole and I can draw field lines for my dipole, and we can actually construct these field lines. So if I draw a dipole field line, I have things that look like this. And these go out here. This would be how a dipole would look. And that gives me these green lines represent my field. So if I look at that dipole, for example, so we're going to do that again. I'm going to draw a bigger set of dipoles here because I want to do a few things with that. So I've got a dipole. And if you go to the PhET simulations or that field visualizer, these are going to help. And when we start to do our electrostatics labs, which we're going to begin next week, we'll start to do our electrostatics labs. We can look at what happens to our electric field. So this is a representation of an electric field around a dipole. Now, if I take a positive test charge out here and I put that test charge right there, we know it's going to be repelled from that spot and it's going to be attracted to that spot. And we can calculate it very much like what we did with our electrostatic forces. But, that doesn't necessarily tell us a whole lot. And we can start looking at our positive test charges and our dipole again. And we can think of our example of Earth. So let's think of our example of Earth. And in that case, we've got a field force, because we've been talking about field forces. And you guys have multiple lectures related to this out there on Blackboard. But I got a field force, and if I did this with a mass object, right, my mass object would be attracted in. And we know that the strength of this force is going to decrease as 1 over r squared. So we get that idea of what's happening there. But now let's think about how we can envision these field lines. Let's look at these field lines. And so if I'm away from my sphere, whether that's a gravitational field or a magnetic field or an electric field, I can look at this and I can put in a plane here. And this gives us our idea of flux. And flux is the number of field lines that are going through this area. I get the number of field lines that are going through that area. So it's maximum when my flux lines are perpendicular to my plane. And if I had a different plane, and I'm going to draw a blue plane now, my blue plane is over here, and it's minimum when my plane, so it's maximum when the plane is perpendicular. Oops, perpendicular, and it's minimum when the plane is parallel. And this gives us our idea that we're starting to play with when I'm dealing with Gauss's law. I'm going to see if I can come up with where we get. And Gauss's law is going to say something to the effect of this, that I'm going to define an electric flux as the dot product and we've seen dot products before. Think of work. And energy. And when we did that before, my dot product was the magnitude of my electric field times the area cosine of the angle, where if I'm in my parallel or perpendicular plane, that angle is going to be 0. And if I'm parallel to the plane, that angle is going to be my 90 degrees. And we're looking at the number of lines through the plane. And so as I look at if I'm thinking about my field lines going through here, if I'm slanted, I'm going to get a different behavior associated with it. Now we can think of a surface, a closed surface, and we can actually get this down to what we call Gauss's law, and you can actually review it in your text. But what it basically is saying is that my flux is going to equal the net charge inside a closed surface. Divided by the permittivity of free space. So if I wanted to find, I've got a closed surface here, I've got a sphere, And if I have an object or a charge in that surface, I'm going to get a field or a flux I'm going to get a flux through the surface. But if I don't have a surface here and I have no flux and the flux is equal to 0, there are no charges inside the surface. So when you guys are doing your homework problems associated with flux, don't let it take you over the top. Flux is actually kind of an elegant solution because basically all we got to do is remember this. And then we have to interpret that to give us some ideas about how charges are distributed on distribution surfaces. So for example, let's say I have a surface like this, and I only have a flux outside the end. Well, that tells me inside of my surface, I have a distribution of charges that are positive because I'm going outward. And that charge surface is perpendicular to the edges of my cylinder. So we can start thinking about how are these charges going to come about and where these charges are going to be. And that gets us important because what's going to happen to us is we're now going to start to think about devices like capacitors. We're going to start to think about what's going to get our charge to move so we can have current. And so this idea behind Gauss's law is really helping us get our mathematics so that we can interpret what our flux is doing and interpret our charge distributions. So let's go back to our Earth problem here. And it gets us back to our idea where that dot product came from. Because remember, our dot product was a scalar product. So my dot product was a scalar product. And what that did for us is, in order to take, if this is a mass object, and I have to lift my mass object of function d, I did work. Remember, work was force times distance, cosine of my angle. We've seen that before. But in this case is where we're drawing our angle to get there. But now I am dealing with that. And I got work, but we also said if that comes out, that force times distance, I got something that we called potential energy. I get this idea of potential energy. So let's look at our situation that we're looking at with charge. So I'm going to take a distribution of charge. Think of a charged plate here. That's positively charged. And I've got a negative plate here. I can draw a uniform electric field. I get a uniform electric field. And in my uniform electric field, if I take a positive test charge, and if I want to move that positive test charge that direction, guess what happens? I have to do work. Because as soon as I put that positive chest charge there, it's going to go right over there. And we get this idea of work, or we get the idea of an electric potential. Which is very, very much like my magnetic potential. It's going to look an awful lot like that. We're going to be able to get a variety of different things associated with that. So it's going to give us our electric potential. Hang on. Which is one of the reasons why we look at flux at that point there. And remember that work was equal to force times distance. Okay. I'm looking at this force. Remember, my force is going to be K Q Q over R squared. But if I'm multiplying by distance, guess what happens? I'm multiplying by an R because that's my distance. I'm going to get my electric potential is going to be very much related to K, Q, Q over R. And we're going to have our R here. We're going to lose the R squared. And we're going to lose our directionality. We also lose our vector character. So we're going to get this electric potential because it's going to work very much the same way as when we did our work and our gravitational potential. But that gets us back to our dipole because I want to show you how that relates back to our field flux lines. Because now, and this is actually how we do things in the real world. If I look at my system here, and I put in a plane here, this is a line of equal potential. The potential along this line is always the same. And we can infer our electric field lines by drawing things perpendicular to our electric potential. And you guys are going to do a virtual laboratory where you're going to look at these lines of equal potential. And you can actually draw your equal potential lines in your dipole and get this represented of our dipole here. So we get a variety of our lines associated with our equal potential. So our equal potential helps us to infer where our field lines are. So we can actually get those field lines, and it allows us to make life a little easier. And it all comes through this idea of electric flux. So we're going to use these electric flux lines to give us this idea that we can move back. But now, if I look at a positive charge here, I have to do work to move it over there. But now we know that that would be a stronger electric potential than if I'm over here, and we can start to see what's going to drive the motion of that particular item. But what's going to be nice now is if I'm looking at my electric potential, and I have this one and I have this one, and this is a negative charge, and this is a positive charge. Here's my positive test charge. And we're going to say that this is 3Q. We're going to say that this is 2Q, and we're going to say that this is 4Q, but it's negative. The potential at this point is just going to be the sum, and I'm going to have my K 3Q 2Q divided by this R minus K 4Q 2Q divided by that R. And if this is an equilateral triangle, that R is there. So I've got 6Q here, and I have minus 8Q there. Well, my potential is going to be a negative 2Q K, that's Q squared, divided by R. And we can just add these up without having to do all of that lovely vector notation. Just like when we were dealing with energy and back in physics 1, we now no longer have to worry about all of those vectors that we were having to worry about with the other items. All right. That gets us our theory that we need. I will be posting some more problems so that you all have problems. I started posting some notes from a couple of my other classes so that I could get you some definite notes. But if we were to go back, I'm going to stop this share and I'm going to come back to the other share. I'm going to share my screen again. Okay. Okay, that worked. I go here. Here is another video on electric potential. This is a video on looking at the electric field. We'll define a capacitance and equivalent capacitance next week. So that's another electric potential problem. This is extra field problems. That's a solution to one of the homeworks. And then in here you have more electric potential. That's conductors and electrostatic equilibrium. This is calculating the electric potential at point P. This is another video to help you deal with that. So that one is a YouTube that's out there. Here is a PowerPoint on electric potential. Here's the organic tutor on the electric potential. And that one's going to go away because that's just an old one. All right, you also have here, those are electric fields and forces. So that helps for that. This is some information on lightning rods. This is why the charge concentrate on a sharp point. And there's some extra homework helps there. So you've got a lot of extra videos on that. So I'm opening up that one, and we will start capacitance next week. And then you've got all of these that are here. And I'll stick around for any questions. Brittany, I do want to chat with you just a second if you're available.